Alright, welcome to the Chapter 6 homework review and welcome to exam week. Very exciting time for all of us. First we'll give you the average on this assignment, which was 9.71 out of 12. So a little bit lower than before, but this does have a lot of material on it, and this one is one that sometimes has a little bit lower scores because there's just so many different things going on. Alright, so we had a few questions to go over today, about 10 or so. Some of them were requests from students, other ones were ones that I identified as being difficult ones for you on this assignment. So we'll go through all of those, and they're kind of divided up into the different topics that Chapter 6 covers, and as always, come find me if you have any other ones that you'd like me to discuss with you. Alright, so the first couple deal with just the concept of dissolving compounds in solution and sort of things about molarity, which is the concentration unit of moles per liter. And so this first question is, which of the following has the highest total concentration of ions? So what this problem asks us to recognize is giving us the concentrations of the solute, but it's asking us to recognize the possibility of these different compounds dissociating into ions potentially when they dissolve in solution. Now the two types of compounds that dissociate into ions when you dissolve them, there's two classes that will completely dissociate into ions anyway. And those are going to be soluble ionic compounds. So any ionic compound that dissolves in water will dissociate into its ions. And then a covalent compound that behaves very similarly is a strong acid. Alright, now strong bases also behave this way, but those are, well, the strong bases that we know are also soluble ionic compounds. They fit in this first category. And then strong acids is a class of covalent compounds. When you dissolve in water, they're going to dissociate into H plus ions and whatever anion comes with that. So those are the two types of compounds that will dissociate into ions, and then when that happens, you're going to get the concentration of each ion is going to depend then on the stoichiometry or the formula of the compound. So if we look at choice A here, we want to figure out the total concentration of ions. HBr is a strong acid, so when we dissolve this in water, we get H plus and Br minus, so it does dissociate because it's an ionic compound. And then the total concentration of all ions, the total molarity of all ions, is going to be the molarity of the solute, 0.05 molar, and then we're going to multiply that by 2 because each mole of HBr gives us 2 moles of ions. 1 mole of H plus, 1 mole of Br minus, total of 2 moles of ions. So the concentration of all ions in this solution would be 0.1 molar. Okay, so that's the total concentration of the ions for part A. Now, choice B was one that a lot of us picked, but it turns out that CH3OH is a covalent compound. It's all nonmetals. We have to recognize that this is not an acid. Alright, so we discussed this in class. When you dissolve covalent compounds in water that aren't acid, you don't get any dissociation. So there will be no ions in solution, and the concentration then would be 0 molar. Alright, so this compound does not separate into ions when you dissolve it because it's not an acid. It's not even a weak acid, it's just a neutral covalent compound. And so when you dissolve this in water, the molecule stays intact, you don't have any ions in solution, and so the concentration would be 0. Choice C, ammonium sulfate, is a soluble ionic compound. All ammonium compounds are soluble. And so when we dissolve this in water, we have 2 ammonium ions in this formula. So that's what that subscript 2 means. So when we dissolve this in water, we get 2 NH4 plus ions. And we get the sulfate, SO4 2 minus. So that means we had a total of 3 ions when this dissolves in water. So the molarity for all ions would be the molarity of the solute, which is 0.04 for choice C. And then we get 3 ions per mole of solute, so that's going to be 0.12 molar. So this one's a little bit higher than choice A, so far that's our highest concentration of ions. Choice D is also a soluble ionic compound, NaCl. We should recognize that all sodium compounds are soluble. And when we dissolve this in water, we get sodium plus and Cl minus, 1 of each. So again, we get 2 moles of ions separating in solution for 1 mole of compound. So the concentration or molarity of all the ions in this solution is 0.1 molar, which is the concentration of the sodium chloride, times 2, or 0.2 molar. So far this one's our highest. And then finally, choice E, aluminum sulfate. So this one is a soluble compound. Most sulfates are soluble except for a few exceptions, and this one would be soluble. And plus we're telling you that it's a 0.03 molar solution, so you don't even really have to think about whether it's soluble or not, because we're telling you by the fact that it's moles per liter that it is dissolved. Now when this compound dissolves in water, we get 2 aluminum 3 pluses, and we get 3 sulfates, 3 SO4 2 minus. So we get a total of 5 moles of ions when 1 mole of this compound dissolves. So then the molarity of the ions would be the starting concentration 0.03 molar, and we have to multiply it by 5 because there's 5 ions that dissociate from that compound. So that's 0.15 molar, but that's still a little bit smaller than choice D. So choice D is going to be the correct answer, the one that has the highest total concentration of ions. Alright, so that asks us to really understand the concept of how these ionic compounds in strong acids separate when they dissolve in the solution and get these different concentrations of ions depending on the formula of the compound. Alright, the next question we'll go to is more of a quantitative question, but it relies on the same concept of an ionic compound separating into ions when it dissolves into solution. So here we're taking 53.74 grams of sodium carbonate and making a solution with a volume of 2.35 liters. We want to know what is its sodium ion concentration in moles per liter. So again, when we're doing problems like this that ask us to calculate a molarity, make sure you know the molarity of what that is looking for. So here's looking for the molarity of sodium ions specifically. So if we have sodium carbonate, which is Na2CO3, and this dissolves in water, we get 2 Na plus and CO3 2 minus. So those are the ions that exist in solution. And what we're looking for in this problem is the concentration of NH plus, the molarity of Na plus. So the molarity for sodium cations is going to be the moles of sodium divided by liters of solution. So that's the definition of molarity, moles per liter. The volume of the solution is given to us as 2.35 liters. And so all we need to do is find out how many moles of sodium plus are in there. Alright, so to get that, we start with the mass of sodium carbonate. So we're looking for moles of Na plus, given that we have 53.74 grams of sodium carbonate. And so the first thing we should do is, if we're trying to find moles of sodium, let's convert into moles of sodium carbonate by using the molar mass. So a mass to mole conversion, the molar mass of sodium carbonate is, hang on a second, so I got 6, oh, that's not right, hang on. Sorry, I forgot to calculate this ahead of time. So the molar mass of sodium carbonate is like 105.99. Sorry, I'm skipping around here. So that gives us moles of sodium carbonate, but then what we want is, again, moles of Na plus. And so what the formula of the compound tells us is that we have 2 moles of Na plus for every 1 mole of sodium carbonate. And it's this step here that most people forget. And that comes back to the concept we talked about in the last problem, where when the compound dissolves, we get 2 moles of Na plus because it's Na2CO3. And so when we work those numbers out, we get 1.014 moles of Na plus. So that's the number we're going to put up here. And then we divide the two to get the molarity. So with this set of numbers, we get something like, once it's 3 decimal places, so 0.432 molar, and we would just enter that into Blackboard. This is a question that had variable numerical inputs, so the numbers that you would have had would have almost assuredly been different than these. a different mass of sodium carbonate, a different volume of solution, but you would follow the same exact steps for getting the molarity, which is moles per liter, but we have to remember that is moles of Na+, which requires us to then do this step there. Alright, so moving on to the next one. Another question about molarity, and this one was a request from a student, and this is a little bit of a tricky one. So what we're looking for is the molarity of sulfate ion in a solution that has 0.186 molar sodium sulfate and 0.0560 molar aluminum sulfate. So again, for this problem, we have to think about what happens when these compounds dissociate in water. So for sodium sulfate, when this dissociates in water, I think we already had this one earlier, we had sodium carbonate, which is the same story. We get 2 moles of sodium plus and 1 mole of SO4 minus. So 1 mole of this compound dissociates into 1 mole of SO4 2 minus. And then for aluminum sulfate, I think this one we also saw earlier, dissociates into 2 moles of Al3 plus and 3 moles of sulfate. So if we're looking for the concentration, what we're looking for is the molarity of sulfate, and that's going to be the moles of SO4 2 minus divided by liters of solution. Now the issue with this problem is that we're not given a volume of solution. However, we're just looking for a molarity, and no matter how much of the solution we have, whether we have 1 drop of the solution or a swimming pool of the solution, the molarity will be the same. So we can assume whatever volume of solution we want to be able to solve this problem. And I'm going to assume 1 liter, because if we have 1 liter of solution, then the molarity tells us the moles of each solute that we have. So if we assume 1 liter of solution, all we have to do is find the moles of sulfate in 1 liter of solution, then that'll give us the molarity. So to do that then, if we have 1 liter solution, we're going to have 0.186 moles of sodium sulfate in that solution. So 1 liter would have that many moles of sodium sulfate. And then from this chemical formula and from the dissociation, we see that there's 1 mole of sulfate for every 1 mole of sodium sulfate. And then we also have sulfate that comes from aluminum sulfate. So in that 1 liter of solution, we have 0.056 molar aluminum sulfate. And that part is going to have 3 moles of sulfate per mole of aluminum sulfate. So this again, 3 sulfates in Al2SO4. Room there, but you're basically going to take the first molarity, and that gives you the moles of sulfate that comes from sodium sulfate, and then the molarity of aluminum sulfate you're going to triple to get the moles of sulfate that comes from that. And so when we add those together, we get 0.354 moles of sulfate. So that's the moles of sulfate that we have in 1 liter of solution, which means we would have a 0.354 molar solution in terms of sulfate. So I think this is a multiple choice question, but that would be the answer you would pick, 0.354. Alright, so those first 3 problems all dealt with the same concept. The next one here deals with precipitation, which is a possible outcome when you mix together 2 solutions of ionic compounds. So in order to think about precipitation, what we need to think about is whether the compounds that formed are going to be soluble or insoluble. So here we have 3 possibilities, and we just have to think about when the ions exchange with themselves. So this is sometimes called a double displacement reaction. When you just when the ions exchange with themselves, whether the products that form are soluble or insoluble. So the first one, we have sodium sulfide and we're combining that with nickel 2 sulfate, which would be NiSO4. So SO4 is 2 minus, that means nickel 2, you'd have one of those. And so then the two products of this are going to be the cation of the first, which is sodium, paired with the anion from the second, which is sulfate. So you're going to get sodium sulfate, which is Na2SO4, correct formula for that. That one's still going to be soluble. All sodium salts are soluble, so we don't have to worry about if that's going to be a precipitate. But then the other product is going to be nickel sulfide. And sulfide is one of those that's pretty much always going to be insoluble. So sulfide is going to be insoluble unless it's paired with one of those special cations like lithium, sodium, potassium, ammonium, those few that we had that are always soluble. So this one's going to be our precipitate. We shouldn't write that as AQ. That was my mistake. We should put that as S for solid. So this one gives a precipitate, so that one we're going to count as part of our answer. Answer choice 2, we're taking lead 2 nitrate. And we're combining that with potassium bromide. Alright, I think we saw almost exactly the same example in class. And when we pair these together, we get lead 2 paired with bromide. So the cation from the first is lead 2, bromide is the anion, so that gives us the formula PbBr2 to balance the charges. And as we talked about, lead is one of those cations that you should look for where just about every lead compound is insoluble, and lead halides being a very classic example. So this one's going to be a precipitate. The second product is potassium paired with nitrate. All potassium salts are soluble, all nitrate salts are soluble, so this one will still remain in solution. It's not balanced as written, but for this problem we don't really have to worry about balancing too much, but this would be the correct way to balance it, is put a 2 there and there. But the point being that we do form one insoluble product, so this one's going to have precipitation as well. Remember, precipitation, we're looking for the formation of an insoluble compound. And then finally for choice 3 we have sodium iodide, NaI, plus mercury 1 nitrate. Now mercury 1 is a weird one. This is one of our polyatomic cations. I don't think I just have expressly talked about this one in class, but it's going to be actually 2 mercury 1s bonded together. So it's actually Hg2 2+. So when we see mercury 1, what that actually is it's a polyatomic cation, Hg2 2+. 2 mercury 1s bonded to each other. And so it's if it's going to be with nitrate, it's going to be NO3 2. Now, whether we realize that little detail or not, we can write the products now are going to be sodium paired with nitrate, the classic example of a spectator ionic compound because sodium is always soluble, nitrate's always soluble. And then the other product is going to be mercury 1, Hg2 2+, paired with iodine. You're going to have 2 of those. And this is one of those exceptions. This is one of the insoluble halide compounds. Remember, for halides, the insoluble ones are silver, lead, mercury 1, which is this one, and copper 1. So this one will also be insoluble. We have to do some balancing here, so I think we just need a 2 there and a 2 there. That'll take care of it. But point being, we form an insoluble compound in all 3 of these, and so all 3 are going to give precipitation reactions. Alright, so some of us might have psyched ourselves out thinking that all of the above can't be the answer, but it was here. And we see that in all 3 cases we form an insoluble compound. Alright. The next question now moves on to the second type of aqueous reaction we talked about, which is acid-base reaction. So here we're mixing together 2 solutions, 30 milliliters of 0.15 molar HCl with 35 milliliters of 0.1 molar NaOH. And we want to know which of the following statements best describes the resulting solution. The acid has been neutralized. We need to add 5 milliliters of acid to neutralize, add 5 milliliters of base to neutralize, or choice D, the solution is basic, the solution is acidic. So in this case, what we have to figure out first is the reaction that occurs between HCl and NaOH, and especially what are the mole ratios of those two. HCl plus NaOH is probably the most common acid-base reaction we talk about in general chemistry. So we're taking hydrochloric acid plus sodium hydroxide, plus 5 milliliters of NaOH, 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 plus 5 milliliters of Na And we see that our acid has 1H plus, our base has 1 OH minus, so that means they would have to react in a 1-to-1 ratio, so we don't have any coefficients on the reaction side. And then the two products, which we don't really need to know for this problem, are going to be water and then the salt, sodium chloride, that forms from the counterions of the acid and the base. So this is the balanced chemical equation, 1-to-1 ratio. And so when we talk about the acid being neutralized, or the solution being neutralized in general, what that means is, in order for choice A to be true, this would mean we need to have equal numbers of H plus and OH minus mixed together. So let's see if that's true. So when we mix these two solutions together, we have 30 milliliters of 0.15 molar HCl, 35.1 molar NaOH. Let's find the moles of each one that we've added. So the moles of HCl are going to be 30 milliliters of that solution. The molarity is 0.15 molar, which means we have 0.15 moles of HCl per 1 liter or per 1,000 milliliters, using the shortcut that I like to take. And so the amount of HCl, or the amount of acid that we've added, is let me try to get that right. 0.0045 moles sorry, that's HCl. I'm getting all over the place here. And then we'll do the same thing for the NaOH, figure out how many moles of that we've added. So in this case we have 35 milliliters of NaOH solution. Sorry. And the molarity for that is 0.1 molar. And so in this case we get 0.0035 moles of NaOH. Alright, so that means choice A cannot be true because we haven't added equal amounts of acid and base. They would have to be in a 1-to-1 mole ratio, and here they're clearly not. There's a little bit more acid than base. So choice A can't be true. The other one that can't be true is choice D, because if we have excess acid, the solution is going to be acidic, not basic. And so really the only answer that would then make sense is choice E, the solution is acidic. Now we know there has to be one right answer. We know that E is true, so we can pick that as our right answer. We should probably verify then that B and C aren't true. Well, the one that we know can't be true is also choice B. Because we have excess acid, if we want to neutralize the solution, we have to add more base to that. We have to get to the situation where we have 0.0045 moles of base. So we don't want to add more acid to neutralize. Now let's verify that choice C is incorrect. So choice C says another 5 milliliters of base must be added to neutralize. We know that we need more base to neutralize the solution. Let's figure out how much more we need. So for neutralization, which means equal numbers of moles of acid and base, the milliliters of the NaOH solution that we need in total, so this is the total amount that we would need, we have, again, 0.0045 moles of HCl, one mole of NaOH per mole of HCl needed. That's the 1-to-1 ratio from the chemical equation. And then finally, if we want to find the volume of the NaOH solution, we know that from the molarity, 1,000 milliliters of the NaOH solution would contain 0.1 moles. And so that means the total volume of NaOH solution we'd have to add would be 45. At the start of this problem, we've added 35, so we'd actually have to add 10 more milliliters to neutralize, not just 5. So 5 milliliters is not enough to neutralize, so that answer is also incorrect. leaving choice E is the only right one. When we mix together an acid and a base, if we have equal amounts of them in terms of moles, we would then expect the solution to be neutralized, but if we have excess acid, it will be acidic, which is the case here, or if we had excess base, it would be basic, and we can figure out how much we have to add by using stoichiometry. So a lot of things going on in this problem, but the only answer that really makes sense is choice E. All right, moving on, the last few questions now deal with redox reactions. So redox equations deal with transferring electrons between two reactants. So one reactant gains electrons, one reactant loses electrons. And this was the newest, this is the most recent thing we did. It's also probably the one that's the most foreign to us. If you've taken high school chemistry, there's a good chance you didn't deal a lot with redox equations as much as you did acid, base, and precipitation. So we're going to do about 4 questions dealing with redox, which is going to be the majority of what we do today. Alright, so the first question just asks us to understand the terminology of redox equations. So we're in a redox reaction, electrons are transferred, and we have from all these different possibilities, from one substance to the other. So let's just look at the definitions that we need to know. Alright. So if the substance is being reduced, or is part of the reduction reaction, the reduction part of the equation involves gaining electrons. So when something is reduced, it gains electrons. Or in other words, it accepts the electrons. The oxidation number when something gets reduced decreases, and the substance that is being reduced is what we call the oxidizing agent. Okay, so that's the part that's, again, a little bit confusing about this. But the point is, there's sort of 3 ways of saying the same thing. The substance that is being reduced, or that is involved in reduction, is going to be the one that gains electrons, one or more electrons. Its oxidation number will decrease, or at least for one of the elements, the oxidation number will decrease between reactants and products, and this would serve then as the oxidizing agent. And then the opposite is true if whatever substance is being oxidized. The substance that's being oxidized is going to lose electrons. Its oxidation number will then increase for one of the elements in that species. And this will then serve as the reducing agent. So when we're talking about redox equations, we're talking about transferring of electrons. And so that means electrons are transferred from the reducing agent, which is the species being oxidized, to the oxidizing agent. And so that's the direction the electrons go, from reducing agent to oxidizing agent. Alright, so let's see which of these answer choices is correct. So choice A, from the substance being oxidized to the reducing agent, those are the same substance. The substance being oxidized is the reducing agent, so that's that one's wrong. Second one, from the oxidizing agent to the reducing agent, that's actually the opposite of what happens. Remember, the oxidizing agent gains electrons, the reducing agent loses electrons, so that means electrons are going from reducing to oxidizing agent, so that one's wrong. Choice C, from the substance being reduced to the oxidizing agent, the substance being reduced is gaining the electrons, it's not transferring electrons from it, so that one's also wrong. From the substance being oxidized, so the substance that's being oxidized is the one that's losing its electrons, to the substance being reduced. So this one looks like it's the one that's correct. Whenever you have electron transfer, the substance that's being oxidized gives its electrons, or one or more of its electrons, to the substance that's being reduced. So choice D is correct. Choice E is also the opposite of what's right. So from the substance being reduced to the substance being oxidized is the opposite. So that one's wrong also. So choice C is the one that gives the terminology correct. So there's a few different ways of saying the same thing in these types of equations. Being oxidized means it's the reducing agent. Being reduced means it's the oxidizing agent. So it gets a little bit confusing at times, but you just want to think about the terminology and just learn it well so that you can answer questions like this. Alright, so in this question we have a redox equation given, and we want to know the element being oxidized is what, reducing agent is what, and the number of electrons being transferred from reducing to oxidizing agent is what? Alright, so we have a lot of different things to answer here. So the first thing we need to do, we're already given the coefficients for this one, so we can just write it out. We have to figure out which species are changing their oxidation numbers to figure out which one is going to be the being oxidized and being the reducing agent. I'll leave these out. We don't care about the states of matter for this. Okay, so the first thing to look at is in this question we're looking for the element being oxidized and the reducing agent. So the element being oxidized should be part of the reducing agent. Those should be part of the same thing. And remember that when we classify something as an oxidizing or reducing agent, we classify it as the entire compound, not just the element itself. So, for example, if the nitrogen was the one that was being oxidized, the entire HNO3 would be the reducing agent, not just the element that's changing. But anyway, let's look at this one here. So copper is oxidation number of 0. It's just a neutral element. HNO3 we've seen a bunch of times now in these redox equations. +1 and -2 for hydrogen and oxygen, leaving +5 for nitrogen. On the product side we have NO, which is going to be +2 and -2. Oxygen is always -2 in covalent compounds. For copper nitrate, we have nitrate is still +5 and -2 for nitrogen and oxygen. Remember, if we just lose a proton, we don't change the oxidation numbers of the other elements. But the copper in this case is going to be +2 because we have copper now with 2 nitrates, meaning it has a +2 charge, and then our friend water +1 and -2. So the first thing we have to do is figure out which element is being oxidized. The element that's being oxidized that means its oxidation number should increase. And if we see what's going on here, we see that copper goes from 0 to +2. So that's going to be, copper is going to be the one that's being oxidized because its oxidation number gets more positive or larger. So the first part of the answer has to be copper, which means we can eliminate choices C and E. And then we're asked for the reducing agent. So the reducing agent is the chemical species that copper is part of. Copper is by itself as a reactant. Remember, oxidizing reducing agents, we're always referring to reactants. So if copper is by itself, copper is also the reducing agent. Species being oxidized is the reducing agent, so that means we can eliminate choice B. So now we have to figure out how many electrons are transferred. And what we see is that we have copper going from 0 to +2. That's a difference of 2 electrons. But it has coefficients of 3, so it's 3 times 2 electrons, or a total of 6 electrons. And conversely, we have 2 of our HNO3s going from +5 to +2, so that's the other 6 electrons that are being accepted by the HNO3. But just looking at that part of the chemical equation, the copper to copper 2+, we know that each of those is 2 electrons. It's happening 3 times, total of 6. So the correct answer then would be A. Alright, so again, a few different parts of this question asking us to identify different features of redox equations, so this was a good one to really drive home some of those key points. The next one here asks us which all of the following are oxidation reduction reactions except. So if we want to identify an oxidation reduction reaction, or what we often call redox reactions, we have to find ones where oxidation numbers are changing between reactants and products, which tells us that electrons are being transferred. So really the rigorous way to do this, I think I messed up the copying and pasting on this one, so I think I duplicated, this is not necessary, this is a duplicate of something, so just copy paste error, so ignore that part of it. Or don't, because I think that was, sorry, that was just my PDF annotator acting up. Okay, so this is, sorry, focus back into me now. So, the oxidation reduction reactions, we're asking for which ones are oxidation reduction reactions. As I said, the long and rigorous way to do this is to assign oxidation numbers for every element in these reactions and then find out which ones have oxidation numbers changing. However, there is a shortcut. So, if an element is present in a chemical equation, it must be a redox equation. It doesn't have to have an element present to be a redox equation. There are a lot of redox reactions that don't involve elements, but if there is an element present, it must be a redox equation, and that's because, as we said in class, elements are the only species that have oxidation numbers of 0. So if an element is changing to something else on the product side, its oxidation number has to change. It cannot remain to 0. And so if we look at this here, we see that this first equation has Br2 and I2, two elements. So this must be a redox equation. We see that Br2 is changing to Br minus, so its oxidation number is going from 0 to -1, and then the opposite's happening for iodine. Reaction B has an element involved in it, copper, by itself, so that must be a redox equation. Reaction C has neutral O2, so it must be a redox equation. Reaction D has calcium and H2, two elements involved, so this must be redox equations. So these first four must all be redox equations because they involve elements, and that means those elements must have their oxidation numbers different between the reactants and the product side because they're only going to be 0 when they're a neutral element. Now this last one here, if there is a correct answer for this question, it better be choice E. Let's verify that this is not a redox equation. It's not obviously an acid-base reaction or a precipitation reaction. There's no precipitation. But let's assign oxidation numbers to make sure that this isn't in fact a redox equation. So HCl is +1, -1. Sodium sulfite, we have +2 for sodium, -2 for oxygen, and that's going to leave +4 for sulfur to balance those out. I think that's right. And then on the product side, we have SO2, -2 for oxygen, which leaves +4 for sulfur. NaCl, +1 and -1. Water, +1 and -2. So if you look at the elements involved in this, hydrogen is always +1 everywhere it appears. Chlorine is always -1 everywhere it appears in this equation. Sodium, sorry, I messed that up. That should be +1. It's 2 +1s, but each one is +1. Sodium is always +1. Sulfur is always +4, oxygen is always -2 everywhere it appears. So none of the elements are changing their oxidation number between reactants and products, so this is not a redox reaction, even though it's not obvious. This would be classified as an acid-base reaction. It does involve an acid and a base, but there's also some other things happening too, so it's not as simple as most acid-base equations, but it is an acid-base reaction. It's not a redox reaction, and that's the one that we would pick. Alright, the next one here, the last one that deals with redox equations, is going to be balancing. So we have Bi3 plus, Fe3 plus in water, and then the products are BiO3 minus, which I think is called bismuthate. I'm not sure that's the right name. We don't have to know that one. Fe2 plus and H plus. So if we want to balance the redox equation and look for the coefficient of H plus, so the first step to balancing a redox equation is to assign oxidation numbers. The ones that are ions by themselves, the oxidation number is just the charge of the ion. We have water, which is +1 and -2. BiO3 minus, you have to think about it a little bit. So oxygen is still going to be -2, unless oxygen is bonded to itself, or fluorine, it will be -2. And then bismuth, if we have 3 -2 oxygens, bismuth has to be +5 to give the sum of the oxidation numbers being -1. Iron is still by itself, so it's +2. H plus by itself, so it's +1. So we find the species that are changing oxidation numbers. Bismuth goes from +3 to +5, and then iron goes from +3 to +2. And then we have to count the number of electrons based on the difference in the oxidation number. So Bi goes from 3 plus to 5 plus, that's a total of 2 electrons, a difference of 2. Iron goes from 3 plus to 2 plus, so that's going to be a difference of 1 electron. We need the number of electrons to be equal between the species that's losing and gaining them. If we want to keep track of which one's losing, this one's gaining an electron, this one's losing 2 electrons. But what has to be true is that they have to be equal to each other. And so if this is 1 electron, this is 2 electron, we have to double the coefficients on iron to make it also a 2 electron process. We're going to put a 2 and a 2 there to make sure that the iron 3 plus can accept 2 electrons. 2 of them can accept 2 electrons to make 2 Fe2 pluses. We keep the coefficients here as 1 to make sure the electrons remain balanced. And now all that's left is to balance water and H+. So as I said, we add water to make sure that the oxygen is balanced. So on the product side, we have 3 oxygens in this BiO3 minus anion. That means we need 3 waters to balance that. by adding 3 waters, we now have 6 hydrogens over here, so we need to put a 6 in front of H+. So the coefficient for H+ is going to be 6. This may have been a multiple choice question, I don't remember, but 6 is the correct answer for that. So that was the one balancing redox equation that we had the most trouble with for whatever reason. So the correct answer, once we go through all the steps, would be a 6 in front of H+. Finally, the last one here is a solution stoichiometry problem. And this is saying if excess zinc metal is added to 100 milliliters of a solution containing 0.7 molar silver nitrate, how many grams of metal will be displaced? Now, we didn't actually talk about displacement reactions in class, and so this type of wording won't be on the test if that was the part that was confusing. So the confusing part here may have been just getting the balanced equation. When we talk about a displacement reaction, what we have is silver nitrate is one of our reactants. And what we do is we take a compound, an ionic compound, and we add a metal to it. So we're adding zinc metal as just a pure metal. And then the products are going to be whatever was an ion, whatever metal was in an ionic compound on the reactant side, silver is going to now be reduced to just silver metal. So that's the metal that's formed. And then we're going to form zinc. Now we have to think about what's the stable charge for zinc. We have to remember that zinc always forms +2 cations. So it's going to be a zinc 2+ compound paired with the anion nitrate, NO3. And then if we want to balance this, we have to put a coefficient of 2 in front of silver nitrate, and its coefficient of 2 in front of silver. So I think probably the confusing part here may have been just balancing the equation. And as I said, since we didn't specifically cover displacement reactions in class, we're not going to ask you to do this on the test, or at least we would, if we asked you to do this type of problem, we would give you the full equation and just ask you to put coefficients in. But anyway, this is the balanced equation, and then from here we just have to figure out how many grams of metal will be formed. So the metal that's formed is going to be silver, and what we have is 100 milliliters of the solution containing silver nitrate. The molarity is 0.7 molar, so that's going to give us moles of silver nitrate. We're told that zinc is in excess. We don't have to worry about the amount of zinc that we have. And so we're going to use the moles of silver nitrate, which we get from the molarity and volume, to figure out how many moles of silver can form, and then conversely how much mass that corresponds to. So that's moles of silver nitrate. We see from the balanced equation that it's a 2-to-2 ratio. And even if you didn't write out the full balanced equation, we should recognize that the moles of silver that we form should be equal to the moles of silver nitrate that we put in, because they both have silver in them. So that's how many moles of silver we have, and then finally we just need the atomic mass of silver to figure out how many grams of silver are going to be formed. So the atomic mass of silver from the periodic table was 107.9. And what we get then, if we multiply out all the numbers, if I did this right, I got 7.55 grams of silver. And again, I don't remember if this was multiple choice or free response, but that would be the answer you would put in either way. Yep, 7.55 grams. Alright, so this is just a solution stoichiometry problem using molarity and volume as part of a conversion involving moles. But really I think that the tricky part here is writing the equation, but as I emphasized at the beginning of this one, we won't ask you to come up with chemical equations like this. We would give you reactants and products, and it would be your job just to balance that. Okay, that takes me to the end of what I wanted to cover today. Hopefully that clears up some things for you. And like I said, if you have any last-minute questions as you're preparing for the exam and going over this assignment or any previous ones, please come see me at any time. All right, and I'll see you guys in class later today.